Hi everyone, it's Michael. So I have a very refreshing problem for you all today. This one was posted by Parmenides on the Art of Problem Solving forum. So he's the source of a lot of the problems on my channel. And it's from the Oral Moscow Team Math Olympiad in 2015. So if you'd like to try to solve it, feel free to pause the video. Alright, so I'm going to go over the solution. So point I is the incenter of triangle ABC, and M is the midpoint of side BC. The line MI meets side AB at point D, and the line through B perpendicular to AI meets segment CI at K. And we want to show that KD is parallel to AC. All right. So when you see lots of intersections like this, sometimes it's a good idea to use projective geometry. So that's exactly what I did here. In any solution with projective geometry, you can usually also do using Menelaus, but projective geometry often makes it easier. Okay, so we want to show that KD is parallel to AC, and one way to show that two lines are parallel is to show that they meet at the point at infinity. So that's going to be what I'm going to try to do here. So what I'm going to do is I'm going to look at the 3 points A, P, C, and we want to show that the intersection of KD and AC is the point at infinity, but we don't know it yet. But whatever the intersection is, whether it's an actual point or a point at infinity, we can take that point and the 3 points A, P, and C, and we can project them through point K. So that's how I'm going to start off the problem, and I'm going to project it onto line AB. Okay. So since I'm projecting point C through K onto line AB, I'm going to let CI meet AB at point F. And now when we do the projection, if we take the cross ratio PCA, and whatever this intersection point is, KD intersect AC, which we want to show is the point at infinity, we don't know yet, but wherever they intersect, we can then project that point through K. So if we take that intersection point and draw the line through K and see where it intersects AB, it'll intersect it at point D. Okay. And if we project P through K, it goes to point B. If we project C through K, it goes to point F, which we just constructed. And if we project A onto the line AB, well, it just stays at point A. Okay. All right, so now we have the cross ratio B, F, A, and D. And now what I'm going to do is I'm going to project those 4 points through point I. So if we really want to use all the information in the problem, it makes sense to also now project through point I. So that's why cross ratios are so handy, because they can tackle problems like this with a lot of intersection points. Okay, so if we project B through I, so the question is, what line do we want to project onto? And I'm going to project onto the line BC. So if we project B through I, it just stays at B. If we project F through I, it goes to point C. If we project D through I, it goes to point M. And if we project A through I, well, we have to draw in that intersection point. So I'm going to do that here. I'm going to let G be the intersection point of BC and AI. All right. So now I'm going to write out the projection. So if we project through I onto line BC, the cross ratio BFAD is equal to BCGM. B stays where it is, F goes to C, A goes to G, and D goes to M. All right, and now this cross ratio looks like it should be fairly easy to compute manually. So I'm going to write out the definition of cross ratio here. So we look at what ratio does G divide the segment BC into, that's BG over GC. And then we multiply by the flip of the ratio that M divides BC into, which is CM over BM. But M is the midpoint of BC, so CM is equal to BM, so that's just equal to BG over GC, okay? And also G is where the angle bisector AI meets side BC. So BG over GC is equal to AB over AC by the angle bisector theorem. All right. So that means this cross ratio is equal to AB over AC. All right. Now we haven't used the fact yet that the line that BP is perpendicular to AI, so we have to use that somewhere. But if BP is perpendicular to AI, which is the angle bisector, then that means triangle ABP must be isosceles. So we have to have AB is equal to AP by symmetry. That's because if you have a triangle where the angle bisector is the same as the altitude, then it has to be an isosceles triangle. Okay, so I'm going to write this out, but if AE is perpendicular to BP and AI is the angle bisector of angle BAP, then it must be the case that AP is equal to AB. Okay, so this fraction is really AP over AC. Okay, so by transitivity, this original cross ratio has to equal AP over AC. Because this cross ratio is equal to this one, which is equal to this one, which is equal to this fraction, which is equal to this, and then you substitute for AP, and you get this. All right, and so now we're almost there because AP over AC, that's the ratio that A divides PC into. So if we unravel the definition of cross ratio, if we take whatever this point is, KD intersect AC, it has to divide the ratio PC in 1 to 1. So it has to, whatever this point is, whether it's an actual point or it's the point at infinity, it has to divide PC in the ratio 1 to 1, but it's clearly not the midpoint of PC. Clearly KD doesn't intersect PC at its midpoint, and so the only other choice is that KD intersects AC at the point at infinity. Okay? And if KD intersects AC at the point at infinity, then KD is parallel to AC, and that solves the problem. So here I just used the really powerful tool of projective geometry. It gives a nice clean solution and simplifies a lot of the calculations that you may otherwise need if you try to solve it without projective geometry. So if you like this video, give it a thumbs up. And if you'd like to see more like this, feel free to subscribe to my channel. Thanks, everyone.